All right, welcome back, everyone. We're talking about lesson 9.5, which regards symmetry. Our objectives will be to identify line and rotational symmetries in two-dimensional figures. And then lastly, we'll talk about plane and axis symmetries in three-dimensional figures. So this is kind of a lesson. There's going to be a lot of demonstrate on the three-dimensional stuff, guys. Once we get into class, I'll have some objects that we can kind of work with and actually have in our hands, three-dimensional objects, and we can talk a little more about axis symmetry then, as well as plane symmetry. But I'll do my best to explain them here in the notes as well. But certainly good to have hands-on time in class. So we'll do that on Friday. So symmetry maps a figure onto itself. So that's kind of our definition here of symmetry. It maps a figure onto itself. A really common thing, and this is at least how I teach when we're talking Algebra 1, and we talk about graphing a parabola. Okay, I certainly show everyone that there's this line that goes through the parabola that we, in Algebra 1, we call that the axis of symmetry, and you can use it to make graphing a little easier, okay? Because if you find a point here, maybe on the right side, you know that it maps across the left side. It maps it onto itself. It has symmetry. Parabolas have symmetry. So this is an example of symmetry that you've already seen earlier in math that maybe, well, now we can connect what we're doing today with that a little more. All right. So line symmetry. A figure in the plane has line symmetry or reflection symmetry if the figure can be mapped onto itself by a reflection in a line called a line of symmetry or axis of symmetry. And this is exactly what we talked about with the parabola just a moment ago. Well, if you look at this figure here that they've got the example for, okay, certainly it has line or this line here, or this axis of symmetry, is in fact, let's make this figure symmetric. These points map across at any point on this figure. It's got a point to the side of it. There. It's got points everywhere that just map straight across the figure, perpendicular to the line of symmetry onto the other side. So that's what line symmetry is. Another really good example, Valentine's Day. You guys, pass out Valentine's cards. If you had a heart, okay, think about having a heart card in your hands here. And certainly, if you took this heart card and you folded it right through here, you would see that card has symmetry. Okay? If you fold over that, it has line symmetry. So that's another really good example. So identify line symmetry. State the figure has line symmetry, right? Yes or no. If so, copy the figure, draw all lines of symmetry, and state their number. So we want to know how many lines. So it is possible that we have multiple lines of symmetry. So one might, start to think about this 1A here, and you might think like, where would a good place to have a line of symmetry? Maybe right through the middle. And certainly you can see this is much further or much closer here than this point that it would maybe map onto is. Okay, that red point is much further than that. So that's certainly not a line of symmetry. We couldn't fold, if we thought of this as a piece of paper, we couldn't fold this over onto itself that way. Can we think of maybe some other ways? What if we, some of us might be visualizing something like this here. We might think, well, what about if I did a diagonal, either of the diagonals? And we got to think, if I folded this over, so I would be going perpendicular to this line. So there, I think about perpendicular. Certainly, okay, not going to map onto itself. It's going to map somewhere out here. And so this one, it actually turns out 1A does not have line symmetry. So there's no line symmetry, no axis of symmetry here. All right, 1B, this pentagon, this looks like a regular pentagon. And certainly if we drew a line here, if we thought about having the shape in our hands and folding it, here, this point would map over here. This point here. All of them in between, mapping straight across. Okay. So this one does have line symmetry. Yes, and it has one line of symmetry. Rectangle. So this is just actually, if you took, your page that you're writing your notes on right now. If you took that, well, how could you fold it to map onto itself? This is rectangle. So obviously we've got two ways, folding paper since elementary school. We got, hamburger method, and then we've got hot dog way as well. So right there is two lines of symmetry. Now, what if we thought diagonally? Well, take your paper and try to fold it diagonally. Does it map onto itself? It does not. So these would be the only two lines of symmetry, but yes, it does have line symmetry, and it has two of them. So a couple good examples there. Let's continue on. All right, rotational symmetry. So now we're talking about, we've got a two-dimensional object, so maybe that piece of paper on your desk, and we're rotating it from the center. Okay, so a figure in the plane has rotational symmetry or radial symmetry if the figure can be mapped onto itself by a rotation between 0 and 360 degrees. So it's going to be between 0 and 360. Certainly, if we took any shape and we rotated it, 360 degrees all the way around a circle, it'd map onto itself. So we want to be between 0 and 360. About the center of the figure, which we call the center of symmetry. So we're talking about the center of this figure. So if we look here at this diamond or this square, maybe more square once we start rotating it. Okay. Again, the observation here, if we rotate 45 degrees, this is what we'd be looking at. So it's not mapping onto itself yet, but if we go the full 90 degrees, where this point now, comes down to here, a full 90-degree rotation, yes, this would map onto itself. All right. So that would happen once. It actually happens every 90 degrees, because if I just keep moving, it would happen. And then one more, it would also happen. So this shape, this square, does have rotational symmetry. Okay, it's got it if we do 90, so that's 1. It's got it if we do 180, there's 2. It's got it if we do 270, so it's 3. And then lastly, if we came all the way back around 360 degrees, it would also map back onto itself. So this shape, it does map onto itself. Okay, and let's scroll a little here. So I want to talk about this next part. The number of times a figure maps onto itself as it rotates from 0 to 360 is called the order of symmetry. So the order of symmetry, notice I was counting these off as we went. The order of this square would be 4. All right, and then we have another thing we can calculate called magnitude. Okay? Magnitude of symmetry or angle of rotation. Yikes. And of course, I'm going to move everything back as well. The magnitude of symmetry, or angle of rotation, is called the smallest angle through which a figure can be rotated so that it maps onto itself. And so the way you find the magnitude or the angle of rotation, just take 360 and divide it by the order. So with that square, we had 360, and if we divide by 4, we would see that the angle of rotation is 90 degrees, which we observed when we were looking at that shape. All right, so let's identify rotational symmetry here. Next few figures. All right, so the center of rotation here would be the center of this hexagon. So if we're talking about this point, well, it would certainly map back on over here. So 1, 2, 3, 4, 5. It would have 6 cases where it would map onto itself. Each time it hit one of these points, it would be mapping onto itself. Right. So it has order of symmetry of 6, and so the magnitude, again, magnitude is just 360 divided by the order. So we'd see the magnitude of rotation, or magnitude of symmetry, would be 60 degrees. All right, we look at the right triangle, guys. We try to pick some point to rotate this thing around, and it's not going to come back to itself until you go all the way around that point, no matter where you put it. So this does not have rotational symmetry. Okay. And if we look here at this flower petal, the petals, we've got these 3 petals that are obviously larger and bigger. So each time one of these petals rotates down to the next position, it would match back up with the smalls also aligning. So this would have rotational symmetry, yes. And the order of rotational symmetry would be 3. Again, to find magnitude, take 360 divided by the order. You can see the magnitude of symmetry is 120 degrees. Right? And so now we're talking about symmetry in 3-dimensional figures. We're talking about plane symmetry, which is just if you imagine, cutting a box in half is what's happening here. It would map back onto itself. It would reflect onto itself. Axis symmetry is when we take objects, we have a cone here, and you can think if we spin it on an axis, so you think your tire on your vehicle, it spins on the axis, it's got axis symmetry. A funnel, obviously the cone, funnel figure, ice cream cone, and things like that. Take a can, could have axis symmetry. Even boxes could have axis symmetry. A rectangular prism, a rectangular box could have axis symmetry if you placed it the axis correctly. So let's take a look. It is possible to have plane and axis symmetry. Certainly, we'll see an example that has both here as we work through these next 2. So state whether the figure has plane symmetry or axis symmetry or both or neither. Right, this first figure, this L-shaped prism, can't really see anywhere where I would, if you thought about putting an axis through here, and rotating it around those 2 points, think about holding that shape in your fingers on those 2 points and kind of trying to rotate. It's not going to have axis symmetry. This thing won't ever rotate back onto itself until you get to 360 degrees. However, taking a piece of paper or a saw or something and cutting this L-shaped prism right through the middle, right there, you would have plane symmetry. You could cut it in half where both pieces would look the same here. So this does have plane symmetry. No rotational symmetry or axis symmetry. Now the regular pentagonal prism, certainly we could cut it in half here, and it would map onto itself appropriately. Cut it in half do that as well. So it would have plane symmetry. Now, would it have axis symmetry? And so this is where you just got to think about, there's not really a lot of pentagonal prisms in the real world, certainly unless you've created one for some sort of unique purpose. But think about, if you placed a pencil through this prism, you put your pencil through it, and could you rotate this thing back onto itself? And if you did it right through the center of that pentagon, the face there, you would have axis symmetry. So this one has both. And like I said, we're going to try to get some more hands-on examples in class of these figures on Friday. So thanks for watching. Everyone have a great afternoon. I'll see you all tomorrow.